part 2 of this video will be a discussion around k-fold cross-validation to check the performance of the model. And cross-validation is a way that you can evaluate your model by splitting your data and having the larger part of your split being used to train a model and then the small part being used to evaluate the model. But the thing is, you're going to do that a number of different times. So you'll split the data in one way, then you'll split it again in another way and another way. So there are multiple random splits, and then you'll evaluate your model. So it's essentially doing the same thing a number of different times. And so it's giving you a really diverse look at your model performance. And so here, to actually look at the code a little bit, we'll first set up some parameters, and that's using the train control function. So we just set it up here with repeated CV, which is repeated cross-validation, and that specific type is k-fold cross-validation. And then we tell our system here that we want it to split 10 times. So we'll have 10 bins, 10 chunks of our data set, and then the whole process will repeat 3 times. And so then the actual process happens, the cross-validation happens with this train function. Again, we'll use our same model, and then we'll use our training data, and our method is GLM for general linear model, and then the TR control value here just refers to our train control. So we just plug in that value that we used. And those are all the parameters for this train function. And then the results that we get are the accuracy and kappa values. And I wrote a note here to myself, but accuracy is a percentage of correctly classified instances out of all instances. And it's useful on binary classification. And essentially for this value, we got a really nice high value of about 93%. And then this other value, it says here that it's like the classification accuracy, except it's normalized at the baseline of random chance on your data set. And it's more useful on problems that have an imbalance in the classes, like a 70-30 split for the classes. Now, if you go back to the distribution of the 2 different classes in our training data, it wasn't really horribly imbalanced. It was 40 and mid-50s, if I recall. So we'll scroll back up and see that here. Yeah, so we see that the Cameo type is about 43%, and the Osmantic type is about 57%. So it's not radically imbalanced. So just looking here at the results from our cross-validation, we got an accuracy of 93 and then a kappa of about 86%. Both of them are really good values. Another check you can do is to look at the ROC, or receiver operating characteristic curve. And essentially you're looking at the area under that curve, and it checks for true positives versus false positives. And so what we're looking at is the value of that AUC, or area under the curve, in this test. And so we want to see a really high number, something over about 0.7. And what we see here is, just skipping to the results, the ROC value that we get is 0.979, 0.98 approximately, which is really good. To set this up, first of all, we'll do another train control function here with some parameters, and then we'll set the model. We'll train it again here with the same model, and then in this case, the metric is ROC. So it looks very similar to what we did previously with k-fold cross-validation, but the setup is slightly different. And the metric here gives us this ROC value, as well as sensitivity and specificity. And that refers to the true positive and true negative. So in this case, we're not looking at the curve itself. We don't have that plotted, although you could do that. But what's important here is that area under the curve. So that value here is distilled. So 0.98, which is very high, very close to 1, indicates a strong, well-performing model. And then finally, the end of this examination of logistic regression for Rice class prediction is to actually do some predictions. So I looked back at the data and then chose some values that looked like they would fall within the data that were in the original data set. So I created a new data set here. It's very small. It has 3 individuals and some values for area and eccentricity. And I chose to put individuals 1, 2, 3 in here, and then I gave them an area of 13, 14, and 15,000 respectively, and then eccentricity values of 0.8, 0.85, and 0.9. And so, like I said, it's a very small fabricated data set, but these values fall within the ranges that would have been found in the original. Now, what I want to do here is create a new column on that data set that contains the predicted class. So in another example, you might imagine that this is a decision to reward someone with the loan or not. So you might say yes or no, or loan or no loan, or whatever it might be. In our case, we want to just assign them the values of the rice types. So here we have a predict function that will take the new values that I'm giving the model, and then it will return the class type that is predicted. And then I simply print out that new data set, and we can see that for individual 1, they're predicted to be of the osmantic type. Same for individual 2, and then the last individual is predicted to be of the cameo type. If you made it this far, thank you so much for being here, and consider liking and subscribing as you go about your day. So I hope you have a good rest of your day, and take care.